Now, there are really three different types of transformations that a matrix can perform. And one of those is called a scale, right? We've seen scale, and we've also seen row swap. And shear transformation we've seen, we just haven't called it that yet. But a scale effect of a matrix could be that we take a vector and we maybe multiply it by say 3. So in that case, all we're doing is we're taking that vector and we're putting together 3 multiples of it, and we end up with 3 times the vector x. It is also possible that we can start off with a vector that is, maybe it's down here, whatever this y component is, and maybe we only change its x component. So notice its x component is whatever this value is, but maybe what I get as an output is not a complete scale of that vector, but maybe all it does is maybe transfers it over like this, okay? And in this case, the blue vector was, again, the vector x, and I guess we don't really have a label for this purple vector, but notice that it has the same y, just a different x, so its x component got scaled, but not its y component. So if I'm dealing with a matrix, recall what we did is maybe we had 4 elements here, and we could take something like 3 times row 1. Okay, we could do that with a matrix, and then we just get 3 times whatever that value is and 3 times whatever that value is, leaving the y values the same. So we could end up doing that. Now, with the matrix containing just 1s and 0s, if you multiply a matrix or any matrix or vector by this quantity, what you get as an output is exactly the same vector. So if I just plugged in some x and y's here, I would get exactly x and y as an output. But if you scale one of the rows of that, say you take 3, 0, 0, 3, 0, 1, notice that all I did was multiply in this, we call this the identity matrix. We'll work with this more later on. And I take that, multiply it by the xy vector. What that will do is it will scale the top row by 3 and the bottom row by 1. You can carry out the multiplication to see this in effect. My point is that if you take the identity matrix and you multiply either of its rows by a constant, it, in effect, when it multiplies a vector, will do the same thing to that vector. We could also perform row swaps. And so if you think about a row swap, if this is x, some x value and some y value, and if you swap those rows, it will switch the y and the x, right? So if it switches the y and the x, maybe I'm not going to draw it quite as proportionally as I did. Maybe we'll make it a little bit more interesting, and we'll say okay, well, did my best here. Let's say this value up here, and this is what my vector looks like, and it's the vector 1, 2. Well, if I switch the x and y components, that becomes the vector 2, 1. Becomes the vector 2, 1. And notice what a row swap does is maybe hard to see, but it actually, when you switch the x and the y, you probably learned this at some point in algebra, it is a reflection. If I can draw that a little more neatly, it is a reflection about the line y equals x. So if I kind of try to divvy this up here, one more time, third time's a charm, right? There we go. That looks pretty good. This is the line y equals x. And this is a reflection. Okay, so basically, if you were to fold a piece of paper that had the 2 vectors drawn like this over that line, they would land on top of each other. It would be perfect symmetry. Now, as far as how that's done with this matrix that we're calling the identity, if you swap the 2 rows, if you move 0, 1 to the top and 1, 0 to the bottom, and multiply this by xy, you get yx as your output. Okay, something to keep in mind. Now, the third kind of transformation we call a shear transformation. And the shear transformation, oh, by the way, just down here, again, just remember that what we're doing is we're just swapping row 1 and row 2. I'll write it like that. That double arrows, that means that we're just swapping them. Again, let me try and make this more neat. It's kind of hard to write with this pen sometimes. R1 swapped with R2. Not much better, but good enough. All right, so here we actually, to visualize what a shear looks like, here we have an image of a sheep, and here is a sheared sheep. So you kind of have to imagine that every point on this is a pixel that maybe starts at the origin and points somewhere. Okay, so maybe you have your origin here, and that vector points straight up like that, and that now that vector actually points slightly angled towards the right. This is what we call a shear transformation. A lot of times it can be confused with the scale effect, but it's not exactly the same thing. So that vector could actually become sheared to become something more like this. So it doesn't have to be in a perfect line either. The height could actually change, but a shear transformation will take place anytime you add a multiple of one row to another. So to see this, if we take the identity matrix 1, 0, 0, 1, and let's say we take row 1 plus row 2 and put the results in row 1. Okay, so row 1 plus 2, row 2 would be 1 plus 0 is 1, 0 plus 1 is 1, and then leave row 2 the same. That would produce a shear transformation, and look what would happen. If I multiplied this by x times y, the output that I would get would be x plus y in the top and y in the bottom, right? Because I've taken x and I've added y to it. So in this particular shear transformation, if you imagine what this looks like, I started off with the vector that was xy, and let's just say for the sake of argument, x and y were 1 and 2. If I now do a shear on this and I add x and y together and make that the new x component, I get 3 for x, the same value for y. So it looks like this. It becomes the vector 3, 2. Now that's a fundamental kind of shear. That just shears it in one direction. But keep in mind that we could have multiple shears. We could also shear in the upwards direction. So the point is you perform a shear anytime you add a multiple of one row to another.